Greetings, this is Mr. Garwood with our continuing video series on Calculus 2nd edition by Briggs, Cochran, and Gillette. This video is going to start section 3.2, and we're going to start looking at graphs of derivatives. In our last video, we introduced the idea that, hey look, if I can in general evaluate for a value of a function's derivative, the slope of the tangent line at every point, and I just use that output, then I have a function. And so today what we're going to do is just like I can graph a function, I can graph the derivative of a function. Before us we have a fairly simple piecewise function. For all values of -2 or less, we're going to follow the rule f of x equals -x. And what I'm going to do is, if you've noticed, I've intentionally color-coded my piecewise function, and you can probably guess that yes, Mr. Garwood is about to intentionally color-code the graph. So this function is doing that for all values less than or equal to -2. And then between, for all values greater than -2 and less than or equal to 0, we're going to follow this line. And in all honesty, the breakpoints are not that important. I could have either way because it's all connected. If we notice, hey look, this is a continuous function because I never have to pick up my pen if I trace over the graph. And then for all values which are positive, so that's starting at 0 and working off to the right, we're following the function -1/2 x plus 4. Now, we talked about that the graph of the tangent line represented the rate of change at any one instant. A really nice thing about linear functions is that the slope of the line is at any particular point. The slope doesn't change. That's what makes linear functions so nice, is that the slope is constant. So what we're going to do is we're going to go back to old school algebra skills, and we're going to talk about, all right, can we figure out the slope of each of these lines? So I'm going to pick any point here on this blue segment. I guess I could call it a ray if I really wanted to be overly specific. But if you notice, for every point I go down 1 and over 1, so slope in the blue term is -1. Now I also could have said, hey, you know, that is, let's see, this y value is 3, this y value is 4, and then the x values for 3, at 3 it was -3, and this one's at -4. So I've got -1 over 1, which is -1. We can do that the hard way. I really like here, we're just going to do this. So the slope of this blue segment is -1. So we're going to go all the way down here, and we're going to say, all right, for every value starting this way, we start at -2, and we kick out now. Mr. Garwood, there's an open circle there. So tell you what, we're going to hold this open circle here. We'll figure it out once we do this next piece. So I'm going to come over here. So I want the slope of our red segment, which I'm just going to represent with a red M. And I'm going to start here. I go, actually we'll do it this way. I go up 1, right 1, so I have a slope of 1. Awesome. So I don't want to talk about what's going on at -2 yet, so we're just going to, or at 0. We got some weird breakpoints going. But we can see, hey look, all these values have a slope of -1 of their tangent line. All the values in here have a slope of +1. And last but clearly not least, I go down 1, right 2. So the slope of this green segment is -1/2. And I can graph it just like we did the first couple. Now, the $10 million question for our video now is, why are these open circles everywhere here where the function changes? Well, a lot like a derivative, or excuse me, a lot like a limit, if the slope from the left and the slope from the right aren't the same, there's a jump here. I can make an argument that at -2, the slope is -1, but I can just as easily make an argument the slope is +1. And now all of a sudden we wouldn't have a function because I would have two outputs for one input, and that's just breaking everything. And we made a big point about, hey, look, the derivative is just a function based on the original function. So what I can now do is I can say, hey, look, well, the function the derivative of f with respect to x, or f prime of x, is the function -1 if x is less than -2. Please note here, I lost this or equal to. It is +1 if -2 is less than x is less than 0. And it is -1/2, and I meant to do this in multicolors and I forgot, if x is greater than 0. Notice I have lost all of these points. The point -2 and 0 is undefined for the derivative because it can't be both. Got to be the blue or the red. It can't be both. So I want to do one more quick example, and I really want to emphasize, hey, look, this has a positive slope, it has a positive derivative. It has a negative slope, it has a negative derivative. Now we're going to talk about what it means if it has a 0 derivative. So we're looking at 3.14, just like 3.13, which is the first one we did. It's on page 115 of your textbook. And what I'm just going to do is I'm going to focus on, all right, where is it increasing? And I'm going to use blue for increasing. And where is it decreasing? I'm going to use red for increasing. And then where is it 0? What does the slope of 0 mean? It's not changing. So here, notice, well, let's start just by looking at some random stuff over here. If we notice over here on the far left, I said blue was increasing. I don't know what it is, but I know that's a positive slope. Just as well as I know that I don't know what it is here. But that slope is increasing. The function is increasing on those intervals. And just as well over here on this far right, I know that everything is decreasing. And I really want to emphasize, hey, look, you know, I don't care where you are, we're always working left to right. So the function is always moving in that direction. So when I say it's increasing, it means as I go left to right, the function's going up. And just as easily I can say, hey, look, that one's decreasing. So both of these have negative slopes. So I would expect on this interval to have some negatives, and here I'd have some negatives, and in the middle I'd have some positives. Well, what does that mean? Well, there's a really cool theorem going on here that says that, hey, look, if I go from positive to negative.
This show, it's not. Oh, I'm sorry.
But if I start positive and I go negative, at some point I have to be 0. And what we see is at local maxes and local minimums, which I'm hoping you talked about in your pre-calc class as well as your high school class, well, there's 3 spots here where the slope is 0. This has a 0 slope, a 0 slope, a 0 slope. So I go increasing, slope is 0, decreasing, slope is 0, increasing, slope is 0, decreasing. And what we see here, if we come to figure 315, we noted that here at these tops, we had a slope that was 0, which means the graph of the derivative should have x-intercepts at those 3 points, at -3, at -1, and at positive 1. And then we said, hey, look, this way and this way, I had positive slopes, and so the derivative is positive where the slope was increasing. And then the slope was negative there and there. So notice, hey, look, when it's positive, the slope is increasing. Or, excuse me, I should say that when the slope is positive, the value of the derivative is above the x-axis. And when the slope is negative, the graph of the derivative is below the x-axis. And this is actually really, really important, that positive slopes have positive derivatives, negative slopes have negative derivatives, and zero slopes, those who have a rate of change of 0, are the x-intercepts of our derivatives graph. So that would be, let's put green x's so they're a little bit easier to see. I hope that you found this video useful, and good luck in this semester.